Okay, everyone. So we'll move on to our next speaker, who is Mark Shannon, coming in from the UK today. His talk is titled "How We Are Making Python Faster, Past, Present, and Future." It's an overview of how we are speeding up Python, including future plans. To introduce briefly, Mark Shannon is a core Python developer and is a creator of HotPy. HotPy is a high-performance machine for Python, and he's also part of the team to make C Python faster. Can I have a round of applause for Mark?
Hello. Do we have slides yet? Yay. Okay, well, you already know the title, so let's get started. If you want to make something faster, you make it get there quicker. But computers don't go anywhere, so I want you to think in terms of time rather than speed. So if we're doubling the speed of something, what we're really trying to do is half the time it takes. This is kind of important because if we want to make something, say, 5 times as fast, it's not, JavaScript engines and the JVM had big speed ups when money was put into them, and often they were going 10 times as fast. So Python is harder to optimize than those languages. So you might think, well, we can do half as well. But half as well as 10 times as fast is not 5 times as fast. It's only 1.8. Because if you think about the time reduction, then if we eliminate half of the orange bar, we've only got 55% of the runtime. So we need to consider all aspects of the runtime. You may have read about just-in-time compilers and various other things, but there's a whole bunches of aspects of running a Python program. There's loads of C code running, garbage collection, and so on and so forth. So if we ignore just 20% of that runtime, it's impossible to get a 5 times speed up. So we need to think about that. Even if we ignore 10% of the runtime, we then need to spend the rest of it up by 9 times, which is going to be hard. So where does the time go? Whoops, hold on. So where's the time spent? That's lagging that, which is not helping. So if you can't read the diagram on the right, the back, don't worry, people at the front can't read it either. What I want to get the idea here is that there are many aspects of the execution time, and we can measure them. But as you can see, they're varied. Different programs use different fractions, but we have to address all of these sort of things in order to speed stuff up. Can we get this fixed? Okay, so a few general principles. Well, the first and most important one is nothing is faster than nothing. By far, the fastest way to do something is to not do it at all. Python is a very dynamic language. It does lots of things that don't really get you to the end result. They're just there for allowing the language to be flexible, introspectable, and so on. And if we can avoid doing those things, we get a big speed up. The next thing we want to do, speculation. And that's about making guesses about what's going to happen in the future. If you're running a loop and you're adding 2 things together, if there were 2 integers last time through the loop, they're almost certainly going to be 2 integers the next time and the time after that and so on. So we speculate about what's going to happen in the future. This is a standard process thing for optimizing dynamic languages, but hardware uses it as well. Hardware often speculates that when you've read 2, 3, 4 pieces of memory, the next piece of memory you'll read is the one afterwards. And we want efficient data structures. Historically, the data structures in Python have not been very efficient. And using less memory is good for CPU caches in a number of ways. It shrinks the memory, so we need less stress on the caches. Things can be in closer to the CPU. But also, we need to make fewer reads to get to some data. So if the data, we have to go through 1, 2, 3, 4 steps, then that's slow, because each of those steps depends on the previous one. CPUs are good at doing stuff in parallel, but if each step depends on the previous one, we can't do them in parallel. So the first thing is I want a bit of history. So this is largely to do with the memory aspect of things. We want to look at some basic Python object. So here's our little example. So we have a class C. Doesn't really matter what the class does. But the point is we initialize it with four variables. We can grab its dictionary and we can see that A maps to 1, B to 2, and so on. Sorry, I'm not very good with this clicker, it would seem. So, oh, now that's out of, hey, right. Now that's ahead of that. It's a little confusing. That's fine, it's fine. Okay, so we have our dictionary. It's got 4 values in it, so it's not a particularly big object. But historically, it's taken quite a lot of memory. So if we go to the picture that we just had a second ago, this was Python 2.7 up to 3.2. Now, the main takeaway from this here is that's a lot of stuff for 4 values. If you look on the bottom right, you can see the 1, 2, 4, and 3. Those are the values we actually we care about. And the rest of this stuff is kind of just extra stuff that that is sometimes necessary, but we don't really want there. So we have the object, which has a garbage collection header. That's so we can find cycles. Has a reference count, so we can know how many references are, so we can eliminate it when it's unused. Class pointer that points to the class. Now, the reason I put the class in green there is just a little circle. Classes are big objects, but we don't care so much about the size, because if we have 1 million objects of the same class, then the class, the overhead of the class itself is barely immeasurable. And even if it's only 1,000, classes might be a couple of kilobytes, but still only a couple of bytes each. So we don't really care about those. And that's the important thing. If we can share stuff, the cost of it is almost negligible. And then there's a dictionary itself. And then the dictionary itself is resizable, and we have to be able to search it quickly, so it needs a table which has the hash codes, so on. But maybe the first thing to note is that all those hashes and keys, all instances of that class in that example I gave you, they're going to share those. So the first improvement we made, which is in Python 3.3, is we got rid of those. And those green keys you can see up there, that's those keys there. Now they're shared between all instances of the class, or at least all those which have the same attributes, which is going to, in practice, going to be pretty much all of them. We have a few tweaks to make sure that is almost all of them, but I'll skip that. So, and you can see that's saved a fair chunk of memory, but there's plenty more to be done here. So the next thing to know is we have these spaces, these values. And the reason we have those is for the dictionary. The dictionary has to use a hash table lookup, and that means it has to be fast. And if it's too crowded, what tends to happen is we have to do repeated lookups to find the value we want. But we can get rid of those by basically using another indirection. So what we do is we put okay, hold on. Is that right? Am I skipping ahead here? Okay, yeah, so we have the keys, right? Sorry, I'm getting slightly out of sync here. Yeah, so we have those shared values, and then we can get rid of those. In Python 3.6, we can move the lookup table into the shared keys so that the table's more compact. And we'll save a little bit more memory there. There's still a few more inefficiencies, though. We've got the alignment here. Now, the reason we need alignment is because this is C Python. So everything has to conform with the rest of C code, which means everything has to be aligned to 2 words. It's just an artifact of the way C works. So we can shuffle things around again. So in 3.8 we do that, and what we do is we shrink the garbage collection header a little bit, and that allows us to get rid of the overhead. But here's a key thing. Every object has a dictionary, but we have the table and the keys already. Now that's got all the information we need in the dictionary. The rest of the dictionary is just management about actually having a dictionary. So effectively, we have a dictionary just so that we can have a dictionary. So in 3.11, we just get rid of that. If you actually need a dictionary, we will create one on demand. In fact, if you only need a temporary dictionary, in 3.13, we will actually remove the dictionary so it goes back to this more efficient form. So here, we just have the values that we need. Now, we've added an insertion order because what happens here is that the dictionary also contained the insertion order. So by pulling the keys out, so they may have one order, and the table may have another. In Python 3.6, the order of dictionaries became a language feature. If you insert things into a dictionary in a certain order, you will iterate them over that order. So we need to maintain the insertion order. But the real win here is not only the lot of dictionaries, but look at the number of reads. We've dropped from 5 to 2. And the reason for that is that the dictionary pointer, or the values pointer here, is now at a fixed offset. So instead of having to go through the class to find the offset and back through the dictionary and then through the dictionary to the table, we can jump straight through the object to the table. And that means that's 2.5 times faster. So that's a big win, both for memory saving and speed. There's a couple of further refinements we can make. We either have a dictionary or the values, so we can use a bit in that to share them, and then that gets rid of the alignment thing. So now down in 3.12, we're down to 96 bytes compared with our, I can't remember how many, we'll see that in a minute, in 2.7. Now, the details, again, there's a few subtleties in order to keep things working and so on, but the important thing here is we're now managed to get the dictionaries down to a reasonable size. But there's still things we can improve. That weak references, most objects don't have weak references, they're very rare. So we could, in theory, store that in an external table and just have a bit in the object to say there are weak references. The garbage collection header can be shrunk. So in theory, in the future, we could have something like this. We can get rid of those values, and we can pack the values at the end of the object. That's a little bit more expensive if we need to resize it, but in most cases, that offers a considerable saving, and it gives the advantage of just a single memory read, which means we've gone from Python 2.7, which had these huge objects with very slow access, to something that is now comparable, although not as fast as Java or C++. Obviously, it's a larger object, but I think that's pretty reasonable. And to be honest, if we can save you the pain of having to write Java or C++, I think that's a price worth paying. But, you know, that's a subjective judgment. So that's a bit of history. So let's look to the future a bit more. Well, there's a little bit more history here, but so we've shrunk the memory use, and can you hear me still? Yeah, that's good. So we've shrunk our memory use. We're interested in making things go faster. And most of the time spent is in the interpreter. That's the bit that just analyzes bytecodes. So first of all, let's have a little interlude. So a quick show of hands. Who knows what bytecodes are? That's a minority. I don't know if that's people just being shy or don't know, but we'll have a quick interlude either way. So bytecode is the actual instructions that the virtual machine runs. So if you're actually, your CPU runs like hardware instructions. Those are encoded in memory. Bytecodes are much the same. They're just a list of instructions in memory that the virtual machine, which is our little interpreter, executes. And it's a stack machine. That means there is a stack of values that we push things onto and pop them off. So take the little assignment y equals x there. That works by breaking it. We broke that down into two instructions which operate on the stack. The first one takes the local value x, that's the load fast 0 in brackets x, and pushes it to the stack. And then the y equals is implemented by the store fast, which pops the value off the stack and stores it into y. Similarly, a plus b here, we load a onto the stack, then we load b onto the stack, and then we perform the binary operation, which takes those two values off the stack, adds them together. This is being Python, add could be almost anything, and then pushes the result back onto the stack. So we have a few improvements up until 3.11, but fairly minor. So one thing that we got from PyPy, which was an alternative, well, still is an alternative Python implementation written in Python, was speed up method calls by, instead of creating the intermediate value of the bound method, we basically skip that step and call the method directly. And we do that with this load method, call method pair. A bound method, if you're interested, is basically if you have a method on a class, you'll often do the name of the instance you're calling, then dot the method, and then the arguments. You can actually assign the dot method to a temporary variable, and that creates a bound method. And this skips that. In the almost always case where we don't actually need the temporary value. And in 3.8 we sped up global variable access, so if you're looking up int or just a globally defined function or anything, and we just use some caches for that in 3.8. Those were small, modest speed ups. So now we'll do a bit of present. So 3.11 and 3.12. 3.12 came out recently. Is anyone actually using 3.12 yet? A few hands. Oh, I'm impressed actually. 3.11, which is a more realistic sort of present. So I guess there's a few more people using 3.11. Hands. And is anyone still on Python 2 out of interest? Good. Okay. All right. So we have this specializing adaptive interpreter, which basically modifies individual bytecodes adaptively at runtime so they can execute a bit faster. And the way that works is we replace individual bytecodes that are very general with bytecodes that are specific. Now, the way they work is they have a check to check that what they expect is going to happen, and then they do the operation. If those checks are correct, which they will be most of the time, as we said, we speculate and we guess that what happened last time is what happened next time. That's considerably faster. So for example, the binary op, if we're adding those two integers together, it's much faster to check if the two values are integers and then go straight to the and then inline the integer addition logic. Likewise, loading attributes. Loading attribute is a many faceted thing in Python with descriptors, and you could look on a class, you can look on the object, and so on and so forth. So that's very important for speculative specialization. So an example here is load attribute class, where we're looking on attribute class. We have load attribute instance. I think we have like 11 or 12 specializations of load attribute. It varies across the versions. If you're really interested in this, and this is an interesting thing, so I would recommend my colleague Brant Butcher's talk. There's the link on YouTube link there, and you're probably easier just to Google. So it's called Inside CPython 3.11, new specializing adaptive interpreter, and that was from PyCon of last year, PyCon US, that is. So what about the future? So we got some fairly worthwhile but not super exciting speed-ups in 3.11. We're nowhere near the speed of the sort of JavaScript engines you have in your web browser yet. So what are we doing in the future? Well, I'm going to give you a little taste rather than try and explain too much here. But let's have this little toy example here. So we have a function add, which adds two things together, and a little tiny code snippet, which basically adds B and 1 and assigns a result to A. And there's the bytecode on the right. The top one is the add function. So we could ignore the resume. That's just an internal bookkeeping thing. So we push X, push Y, add them together, and then return the result. And our little snippet here loads the global add. So add is a function, which means it's stored in a local global variable. We push the local push 1, call the function with 2 arguments, and then store the result. So the first step is what we do is called region formation, which is basically where we try and get a chunk of bytecodes to optimize. And the first thing is we can notice here effectively what we've done is inlined that function. So we've merged the function into the sort of calling code. And the more observant of you may have noticed that this code has a call and a return. But this function has a push frame just above the green section and a pop frame. Because we've inlined it, we no longer need to do all the call logic. All we need to do is make space for the new local variables, and that's pushing the frame and popping a frame. Anyone seen a traceback? You'll see a list of where you were in each thing, and those correspond to a frame in Python. So the next thing is specialization. Now this is very similar to what we did in the for 3.11. So basically, we converted the binary op into binary add, into 3 parts: a check where we check the top of the stack and the next value on the stack are integers, and then we do the integer addition. If those checks fail at runtime, we have to exit the code back into wherever we would have been in the original interpreter. Now, the next thing, and most sort of powerful thing, although unfortunately we haven't really started implementing this, but hopefully we will have this in for, well, we will have something in for 3.13. Obviously, probably not complete, and there'll be future improvements as we go through later versions. But we do what's called partial evaluation, and the idea is to evaluate whatever we can up front, so we don't have to do it at runtime. So we do one optimization pass where we evaluate as much as possible at that time, and then all the many thousands, we hope, of subsequent executions, we're not doing that work. We use a technique called abstract interpretation, which basically means we interpret it sort of at the time in the abstract. So the code on the left was that bit I just showed you where we inlined the call. And on the right is the sort of minimal version we can sort of get away with here by basically not doing anything we can get away with doing like up front at runtime. So for example, the load global. Well, we don't actually need that load global because we know what the function is, provided no one has overwritten that. And what we can do is we can add some machinery to the dictionary so that if someone stores that add, we throw away all the code on the right and just go back to the normal one. And because we can do that, we don't need to evaluate that load global because it's effectively a constant now. That check, we don't need to check as a function because we know it's a function. And then basically we essentially do the same all the way through, basically postponing the evaluation of something until we need it. Which is why, if you notice carefully, you'll see that the check and the load const are differently ordered because it's the check that forces us to load the B because we can't check it's an integer until we actually have it. So effectively, we just don't do anything until there's actual code that forces us to need it. And it's the int add, really, that forces us to do the work, because we can't add two integers together unless we have them. So effectively, all we really need to do is do the actual addition here. You'll notice the little arrow here. If the check fails, that's a little bit of cleanup code. We now need to restore the state that the program would have been in when we got to that check, which means that we need to actually load the function add, and then unfortunately, because we've loaded it after B, we're now in the wrong order, so we need to swap them over, and then the exit goes back to the normal interpreter. So we now have efficient, compact bytecode, but it's still bytecode, we're still interpreting it. And that adds quite a lot of overhead. So what we now do is try and convert it to machine code. There's a technique called just-in-time compilation. And we're going to use a technique which is called copy and patch, which is a sort of modern variant on an old technique. The old technique being a templating compiler, and I'll show you the difference in a second. So I don't know if anyone's familiar with C code, doesn't really matter. So here's the C code for the load fast, which is the code that takes our local variable and pushes on the stack. And that code does exactly that, plus it increments the reference count on the object so that for memory management purposes. Now, if we run this through a C compiler on high-level optimization, this is actually from Clang, but if you run it through GCC or MSVC, you'll get something fairly similar. And this is for Intel x86-64, which is not the most readable machine code, but it's machine code, so it's never readable. And the only thing I really want you to point out here is that little blue box up the top there. The rest of it is just machine code, and it's opaque. The C compiler generates it. We look at it out of curiosity, but we don't actually care too much as long as it's right, what it does, how it works. And this is where the copy and patch comes in. So imagine we have a sequence of bytecodes like load fast 1, load fast 2, load fast 3. We're loading 3 values onto the stack in order to call a function or something. The way we compile that is we basically copy that chunk of code 3 times for the load fast 1, 2, 3, and then we patch them. And that's where the oparg thing is. So basically, we have linkage information, which is something the C compiler uses after it's compiled to an object file and linking. And that allows us to patch the code. So where that oparg is, we'll patch in 1 in the first one, 2 in the second one, and 3 in the third one. And that will give us machine code, which is equivalent to the bytecode, but noticeably faster. The reason it's faster is because in the interpreter, there's quite a lot of dispatch overhead, and that's roughly equivalent to that machine code there. So it can effectively double it in speed. So that's a whirlwind tour of a whole bunch of optimizations. So if you remember, I said there's a whole bunch of aspects of the interpreter. virtual machine, whatever you want to call it, that we need to consider. And we have this sort of like range of optimization techniques. And we hope that if we apply all those optimization techniques, we can basically reduce the overhead of enough parts of the virtual machine to get the sort of speed ups we desire. So like we have 5 things here where I've listed the sort of things we want to speed up. There's the bytecode interpreter, dynamic features, that's just Python being dynamic, memory management, the cycle GC. The cycle GC is actually a surprisingly expensive operation, but it's very important. So CPython has reference counting as its memory management system, but reference counting has a weakness. That if you have an object A that refers to B and an object B that refers to A, that forms a cycle. That's uncollectible. You can't reach it. You can't reach it, so it's used as garbage. But we can't collect it because both A and B have a reference count of 1. And that's where the cycle collector comes in. That sort of backs up the normal reference counting thing. And then C extension code. I imagine plenty of people here use endless C extensions. So basically, I mean, NumPy, there are many, many C extensions. And there are 2 things that they spend time doing. One is actually useful work. Well, that's great. But the other time is interfacing with Python. C and Python have like different ways of doing things. You know, you have to box integers, unbox integers, make calls, calling conventions, and so on. So that's quite a lot of overhead there. But the techniques I've shown you apply to many of these things. So the bytecode interpreter, which is the biggest user of time, is the one we want to speed up, pay most attention to speed up, but we mustn't forget the other things. Partial evaluation and compilation to machine code give us a big win there. The specialization reduces the overhead of the dynamic features. Although the specialization occurs in the interpreter, the win is actually outside of the direct bytecode interpreter because we avoid making calls into the C API and doing lots of work there. We have better object management, so that reduces better object layout, as I showed you earlier, reduces the memory overhead, both in space and the amount of time taken to it. Partial evaluation and unboxing also help there. Cycle GC, again, the better object layout, and a thing called incremental collection, which is where we do a little bit of collection at a time. And finally, C extensions. This is a hypothetical future where we basically have a lower level C API. So the C API can express its like C-like API rather than the Python-like API. And then the virtual machine can adapt to that to reduce the overhead of calling into the C extensions. So what's coming in 3.13? Now, no promises here because we've barely started working on 3.13, but we have a plan, we have good estimates of what we want to do. So this is a tier 2 optimization, optimizer is the main thing for 3.13. And that is the partial evaluation and the JIT compiler that I've just explained. I'm going to make a wild guess here and say between 20 and 40% speed up. I'm hoping nearer 40, but we'll see. So, conclusions. Python is getting faster, and we expect it to keep getting faster. So, if you want to save money, reduce energy use, keep up to date, just upgrade to the most recent version. I mean, it's probably good practice anyway for all the security reasons listed, but it'll also save you some money. Thank you.
Thank you.
Mark, your argument that a 1.8 times speed up is half as good as a 10 times speed up completely lost me. Would you care to revisit that?
Okay, of course. So, I'm going to have to press this button a lot. So, in order to get a 10 times faster, you have to remove 90% of the execution overhead. Half of 90% is 45%. That gives you down to 55% of the time, which is 1.8 times as fast. So that's the time spent. The blue thing is how much time we need to spend if we want it 10% faster. If we do half the work, the point is, the work spent, the effort spent, what we have to do to make something faster is about removing things, not adding things, really. I mean, we add a bunch of code in order to remove runtime, but it's the time. So each of those little boxes is like, we do a bit of work to remove that. To get to 5 times fast, we have to keep removing those little boxes until we've removed most of them. So if we do half of them, we're there, which is 1.8 times as fast.
Okay, folks, we don't have time for any other questions, but I understand that speed and Python, a lot of people are very passionate. Another round of applause for Mark.
Thank you.
Thank you very much.